I quite often buy a baked potato for my lunch at work at a place where they give you one of these plastic forks to eat it with, and with monotonous regularity the fork breaks. And I suppose that doesn't really matter all that much. On the other hand, if you make these, then it matters a very great deal if something goes wrong with it in service. And the same is true, of course, for anything that's very large and expensive and has massive consequences if it goes wrong. People in these businesses that I work with set a lot of store by having computer simulations of the things that can go wrong, and usually they've got a very large bank of results from simulations to cover all sorts of operating conditions. And if ever something very occasionally does go wrong, they're very, very anxious to be able to calibrate the simulations and the models based on the data they get from the real incident. But of course the simulations will never cover exactly the design point or the operating condition of the simulation. And so you come down to an interesting question, which is how do you choose the simulation which is what you believe to be the best fit to help you calibrate your model? In this little talk, I'm going to talk about a graphical user interface created in some software to help somebody do exactly that in the aerospace industry. But I've altered the software, and I'm going to present the demo pretending, if you like, it was in the oil and gas industry. The lessons and the message are exactly the same, but it protects our clients' confidentiality. So the kind of variables you would have in a simulation of something going wrong, or a leak, for example, in a plant like this, might be the flow rate that was going through the pipe, and maybe if it was multi-phase, what proportion of it was in the liquid phase. There might be a parameter about something to do with the gaseous part. There might be some environmental parameters like the humidity of the atmosphere. So the problem we have to solve in our software tool is how do we help a person choose the simulation that was a good fit to those parameters? And it's a scale and complexity problem. Often there'll be a large number. In this particular project, there was 20,000 simulations to choose from. And essentially, it's choosing something in kind of a six-dimensional design space. And that leads to the nub of my message here, because as soon as you realize that it's a six-dimensional choice problem, as an engineer, you tend to think, oh, that's a pattern, I recognize that. There's lots of very good solutions that have emerged from other people about how to help somebody navigate in a six-dimensional space. It's to the point that you can go out and buy software to help you. I think this is something I picked off the internet, and it's to do with chip cooling, and it shows the sensitivity of the solution to a whole set of input variables. But the point I'm going to try and draw out is that our instinct to recognize it as a pattern and then choose solutions from the domain that exists for those patterns is perhaps sometimes leading us astray, and that we can do better if we start from first principles. So for this problem, we could imagine talking to a user of this software and saying, pretend there's nothing and you can just make up whatever you want, a kind of fantasy solution. What would it be like? This is not to suggest that we'll very often be able to produce the fantasy solution, but it helps to align our understanding of what it could be so that we can get close to it. And in this particular case, the user said, well, to be honest, the first two things we'd focus on, really to the exclusion of the other things, is the flow rate and the phase mixture. Most of our simulations are at fixed points in those dimensions, and so we would usually choose on that basis first. Maybe we could choose from points on a 2D graph. There's a slight issue that there could be simulation results which have an additional parameter varying, which we'd meant to choose between. So this is what we came up with to solve the first part of the problem. You can see this graph area here at the top, and the crosshairs represent the real incident that the person's trying to match up. And they might decide that to get as close as possible to the crosshairs, they might choose, say, this point. That might be a reasonable trade-off for how close you can get in both two dimensions. And when that's selected, the user said, well, we want to have a second down selection once we've done that, which is just a discrete choice between what's actually available. And in this case, we've got identical flow rates, identical phase mixes, and the only difference is this gas property. So we might choose, for example, that one. Now, that's helped us down select already from 20,000 cases to, you see here, 209 cases. But we've still got some choices to make that we can guide the user. And in this case, we've got three variables here, humidity, severity, and wind speed. And they each have a target value and an error band, which is huge, 55%. And we can see that with those particular error bands, we're narrowing it down to 200 odd results, which is too many. But the reason it's been presented like this with the sliders is because the users said they wanted to be able to get a feel for how much data there was available, depending on how stringent they were on each criteria. So if you plot this number here, 209, as I gradually tighten up this, you'll see that I can move it in real time. like this, and you'll see that we're now down to 130, 108 and so on. If I go right down to there, I can see it get cut off to 0, and I can get a feel for how much data is available. Maybe I'd leave it there where I've still got a fair amount of choice. I might then look at the second area of sensitivity and gradually tune that one down to see. So we're down to 27, naught, so I think probably we might choose, or maybe there. And then finally I can experiment with this parameter and see how much latitude I've got. It's come down to 15 already. So I'll probably leave it there, having chosen 15, and probably come back to this one to tighten up a bit more. And there we are. That's brought it down to 5 choices, which is manageable. These abbreviations are something that people working with this software, they would mean something to them, and they would choose one and submit. So that's the end of the GUI demo, and the point I'm trying to get us to reflect on is that as engineers we are extremely attracted, normally I think, to patterns. We celebrate patterns. We say if we can recognise our problem as being one of a certain pattern, then usually we can draw on some solutions in that space which other people have worked through and thought through and have proven the test of time, and usually that's the right thing to do. But interestingly, with a graphical user interface, if you take care to ask the client or the user what they actually want, their fantasy experience, sometimes what they want is not really a pattern, and in many ways what I've just shown you is a bit of a hodgepodge really of idioms. There's a graph, there's a pop-up menu, there's sliders, there's clicking, but it's exactly what they want. That's as close as possible to the way they want to think about the problem. And so sometimes abandoning patterns and just thinking about what we could do produces some very interesting results. And I'm hoping that will stimulate thought in other areas. Thanks for listening.